we are understanding that LLM can really assist you to do the design space exploration. Okay, so there's a lot of augmentation with generative AI, that in two ways. One is that you just train a deep learning neural network to do the design instead of generating all the code. Just say, I want just a very rough estimate of how the exploration will happen, or actually generating all the codes and doing the generating all the code, and then actually having the this approach to uh, uh, and using the LLM. So I also thought that because you are using LLM for everything, so you need to know its limitation as well. So only if you know its limitation and how it works, then you can best use it. So LLM, as uh, we know the neural networks, and I covered this a little, that neural networks are where it has multiple layers, especially a deep neural network has multiple hidden layers, and they are, most of the time, they are fully connected layers. You put an input, and if it is a classification problem, it'll give you an output. If it is uh, a regression problem, it will give you a value, or where you're predicting something, it can also give you a value. So it depends that how you're using this neural network. Usually, neural networks have all these parameters, and we will cover a few of these. The weights are called the parameters, which you train to get the desired answer. So these weights, they vary from billions of parameters to trillions of parameters. So it's very expensive once you are using an LLM. And then there are a few which are open source, and the other which are closed source. So OpenAI is supposed to be open, but it is actually closed. So, but Llama is an open source LLM. So the availability is of the architecture and all the weights. So the weights are the main thing. Sometimes they keep it very secret to their hearts. They will never tell that how they what the weights are, because the magic is in only in these numbers. So, for example, if we take the example of Llama 3.1, uh, it has been trained on 10 trillion words. Those were in the training sets. So humongous a lot. It has taken it 16 days, 60 days to train the network, and about 20,000 NVIDIA H100 GPUs, and these are very, very expensive too. So the non-recurrent engineering cost is humongous, and then the computing costs. So it's just this day, these many days, and this much of NVIDIA power is about $30 million of just the training bill, not the hardware. Hardware is even more expensive. So it's very, very expensive to train such a model. Uh, and these are the weights that are used to compute the response. And sometimes they can make, and again, if like just for training requires that much, is inference also required a lot of many GPUs, because every word it generate has to pass through all these parameters ideally. So if it has like 70 billion parameters, each word that you are generating through the the Verilog code, it almost passes through all these parameters. So ChatGPT 3.5 required about perhaps 10 A100 GPUs to have an inference. So it is costing them a lot of money, and they're spending a lot of power to provide you with this facility that you can go. And so it's not like magic without a cost. So if they start charging you money, so you may say, I'm not going to generate the code using LLM. I would rather do it myself, because it's expensive to do the inference. So the cost is important. So sometimes because these parameters and most of the multiplication additions are floating point, and so sometimes they do the compression of weights, they do the quantization. So play with this so that they can reduce the amount of computation required in the inferences. So Llama 70 billion requires 70 billion floating point 16-bit numbers. So you can see that how many of these numbers and how big a file is, which are just the parameters. And if you quantize it 4-bit, why quantization? Because end of the day, whatever you input to an LLM, it only generates one word, and it means it only generate in a dictionary of vectors. It generates a number which points to a vector. Okay, so they say why to have like 16-bit precision, whereas end of the day you are only going to generate one number, which is an address of a vector in a dictionary, which primarily is a word, next word, and that again. So sometimes they play with the quantizing these numbers to smaller numbers and see that if they can still get a good answer to the problem. So LLM that we have been using, especially the Chat GPT, the Gemini, and even the uh, uh, Meta.ai. So every model is generating, and then there are like some which are fine tuned on Verilog. Then there is a RAG, which is where you, if you have a big code repository and you don't want to share it and you don't want to tell LLM to train on that, so you can also make use of it, the code base that you have in your company, in your organization, in your university. So this is where the LLM fits in. It's broader is AI, then is machine learning, a subset is deep learning, then is generative AI, then there has been a natural language processing, and so it is like combination of deep learning and generative AI and natural language processing. And this is kind of a history where most interesting things have happened after uh, Chat GPT 3.5 was announced, 175 billion parameters. And then Chat GPT 4 was announced. It uses 1.7, it has 1.7 trillion parameters. And now Llama 3.1, which is an open source, is announced, and this finest version has 405 billion parameters, and it is open source. So from EDA perspective, what people have been, so there's a lot of excitement in electronic design automation industry from multiple perspective. Okay, one perspective is that you're generating architecture, you are generating codes, you are debugging it, you are doing IP integration, you're doing design verification, and we have seen kind of all of this. So you're doing a lot of creativity, and that is driving innovation. But on the other hand, also you are your own IP. You do the catalogation, catalog your IP. You do the product documentation. You know, or onboarding of new hiring, and so you are also doing training, support, and something very boring which nobody wants to do, like the documentation. Nobody puts comments, so you ask, "This is my code, please comment it." And the status summaries, the log file analysis. So this is the boring task, and usually people don't do it. And because they are not doing it, so they uh, uh, end up very difficult for people who you are onboarding to understand the code, and especially Verilog code is very difficult to understand as things are happening everywhere. And if you're not a good coder, it'll be very hard for anybody to come in and understand what you have developed. So LLM kind of, as I mentioned earlier, and this is again, we need to remember that it uses the just generates the next word. This is the context window. There's a context window, so you can put a story, and it depends how good a story you put in there. It'll try to understand everything that you write in your prompt. So that's why the prompt engineering has become an area, that how good a prompt that you write, and and once you write it, it will try to generate a word at a time. So once you write a quick brown fox, and it has learned it should write jumps. And now this becomes the context, and it generates the next word over. Now this whole thing becomes the context. And so you just keep on building the context and keep on generating the next word, the next word, the next word. Okay, so from these words, you just start generating, but it generates one token at a time. So there is a pre-fill. A pre-fill is just going to fill whatever you provided, and then from the pre-fill, it'll try to generate just one word. And so one word, and that word will come back and will increase the context. So usually once you are using a chat bot or something, there is a system prompt, which basically say it's a chat bot and you should just answer the questions. But from here on, it is the user, that user is giving a prompt. So there's a prompt window, and important is the context window length, because end of the day, it's a lot of hardware, a lot of memory that is going to be there to prompt to use every token, every word in your prompt. So you cannot make a very big prompt as well. So there is a constraint, and this constraint is increasing every passing day. That how much the context you can put to a large language model. So that is your prompt. And once it generates a response, and that's how what I have been using, it also becomes part of the, if you are using the same context, your response also becomes part of your prompt, part of the context. So that's why you can go in the memory and keep talking to your LLM. So say do a little and then ask it, because it becomes part of the prompt. Say, oh, use this, but I want you to add into this, so it'll increase. Then you say, oh, it is good. Use this and add into this. So you use this prompt cycle intelligently, but also remember every LLM has a context window overflow problem, that if you're putting a lot of it in the context window, it start forgetting. It'll throw the oldest thing out. So it's kind of uh, uh, a first in, first out buffer. So it'll just throw out the older thing. I'll just put the newer thing. So LLM forgets earlier parts of the conversations unless action is taken, or you just have some condensed thing that you are using it. But this is important, that the prompting is important, that how you intelligently prompt it, and how you use the response of the previous prompt to generate another prompt, and response of the previous and the previous and the prompt and this prompt to write another prompt. And that's how we successively build and generate our answers. Okay. So prompt engineering, perhaps I am just teaching another course there. I'll spend perhaps a complete lecture on how to write good prompts. But here, remember that you are writing a prompt, so you want it to, for example, sometimes you say, just be a Verilog front end developer, generate a course. You give it a role, and generate or verify or compare, or so you have some action words. You always want it to do something. uh, and what do you want to, you want RTL focus, or you want stimulus focus, and you can ask questions, and you can also give this is the expected attributes that you want. So there's a lot of things that don't do this, don't do this, use a neg edge reset. And so you can just ask it to uh, so you really need to just say whatever you want to say. Just don't write a single line, generate this for me. If you let me show you some of the prompts that I was showing you earlier, if they are still, yeah. So sometimes you have to just tell it a bigger story like this. Design a module RTL Verilog design of something, maybe an advanced adder like carry select adder. Now generate its stimulus such that the stimulus automatically check the answer of all test vectors using the functional description of the adder in the test module and display an error if the two outputs are not matching. So this is the prompt that I have written where I've said this is what I want you to do. Okay, and step do this, generate a model, then this, check the functionality, generate an error, display an error. This is how I want to see my output. So, and still, if I'm not happy, as here it generated perhaps a 4-bit adder. I said no, generate. So this is the test bed. And then I say, can we generate code for a multi-bit carry select adder in the module to make the example more interesting? It says, okay, certainly let me do that. So it has now a 16-bit carry select adder, and it then has generated the error code. And okay, so then I am just doing other stuff. And so, so this is how you write and context. I have already explained you what is context. Okay, so sometimes you have a context that for other type of prompts that I am uh, just going to Singapore, and there I am expecting to meet with some of this, and in my meetings I want to give them a brief of the course I'm teaching, for example. So you just give the context under which you want, and I'm teaching a class where I have students, and the students have no background on this, so I want to make them learn. So you generate a context, so it will help you to primarily do that. And now, very quickly, again, though this is a bit more complex, I don't want to get you into the complexity, but how this whole thing works, so that sometimes people don't know how it works, honestly, how it actually able to generate, such a good uh, everything. Like, how can language model generate Verilog code? Sometimes is very mind-boggling, and especially once you give it an error that you are getting and it'll correct it. So it's very mind-boggling that how it works. So it's like something which is called self-attention. So there was a paper, the transformer paper, which perhaps is the most and most instrumental paper, which has triggered all the development of this large language model, which says attention is all you need. So attention is all you need. A very crazy name for a technical publication by Google, which has like transformed and has brought all this into the realm of practicality and attention. So need to understand what attention means. Self-attention means. Self-attention is like if you have a word, okay, I swam across the river to get to the other bank. If you look at this bank, independent of what other words are in the sentence, you may assume that bank is a commercial bank. Okay, so it is only the other words in the sentence which will help you to understand the context of a bank. Okay, so and somebody says a word is known by the company it keeps. So this is perhaps the most important thing, that all large language model, once you give them a context, they will try to understand the entire thing that you put in the context into the prompt, every word, every sentence that you write, and they correlate them with each other. Okay, they say, okay, I swam, and because you swam across the river, and then the bank, and then it will the LLM will able to understand that you're talking something about uh, uh, a bank of a river, not a financial institution, and it is based on somebody who said, "You shall know a word by the company it keeps." So that's why the prompt, how intelligently you write a prompt becomes very important, because every word that you write and the relationship of this word with the other words in the sentence and the sentences, so it will try to comprehend all what you have written and then it will generate a word out of that, and that word will come back and again becomes part of this whole thing, and it'll just keep generating word after word, word after word, and trying to understand, comprehend by having this mechanism of self attention. So the bank highly correlate. If you say I drove across a road to get to the other bank, then it would say, oh yes, it's actually a financial institution because the road and drove is is a financial institution. So the context matters, and while you are writing prompt, you need to make sure that you write a beautiful prompt that should help uh, the 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 large language model to generate the next word which is right. Okay, and it is not looking, and remember, it is not looking into any document, it is not fetching a document. Okay, it's not fetching a document, it's just a neural network with a few billion or few trillion parameters, and your all this context is moving through the layers, through the layers, through the layers, and generating just a vector which points to the next word. So the context matters a lot. So, how do you basically, how the self attention works is simple, that somehow you need to find out the correlation of words in a sentence with each other. And that's why it is called self attention, because you are not finding their relationship with some other sentence. It's like, so it's kind of a matrix where you write your sentence here and you write your sentence here, and then try to find out how close Swam is to the bank, how the which words are closer to each other, and they relate, so that I'll try to comprehend uh, the the word. So to do this, because you need to find the correlation, and we may say the dot product, you need to somehow convert this into math, because it is very difficult to find correlations between words, because this has no understanding. So somehow you got to represent every word as a vector in a vector space. Okay, if it is a three-dimensional vector space, so the entire dictionary will be a position in this room. Okay, every word will have a position, and that's how you will able to find out the correlation, how close a word is from the other, by finding simple a distance or a dot product of the two vectors. If they are closer, if they are in the same line, so you know the dot product is going to be maximum. If they are opposite, dot product is going to be zero. So the first task definitely is that how you place these words in this space, and that's what is the core, the base of all language models, that all these words are placed, those which relates to each other, closer together, right? So the self-attention mechanism is to add contextual information to words in a sentence, and and that's how now it does it like this. So every word, the sentence is broken down into tokens. Usually token, a word is a token, other than there are words like high, higher, highest. So it will say high is a token, and EREST, so it will be another token. So to reduce the number of tokens, it would have most of the words, which are singular words kind of, they will be an independent token, and some it will split into two tokens. So, and then every token is converted into a vector. So the very first thing any large language model does is it's called word embedding. Okay, so word embedding is where every word is converted. Now it is language independent, kind of. It does not matter whether it is Urdu, Islamiyat, Arabic. It does not matter. So uh, what matters was here that how you build this word embedding of Urdu, word embedding of Arabic, word embedding of something. So Verilog itself kind of is not a language. Maybe somebody may try using Verilog as a language and seeing the correlation, training the whole LLM on Verilog. But it is not trained like this. It is just Verilog has come to an LLM as text, as other languages. So It is just converting every file which it has used for training. It has converted every code that is written into first tokenize and then vectorize. Okay, so the vectorization happens. So now here every word is a vector. Like this word will be a vector. Depend different LLM have different dimension of this vector. Like chat llama 3.1, the length of this vector is 4096. Okay, 4096 element vectors. So it depends whether it is 50 dimension, 100 dimension. So every word then converted into a vector of 4096 dimension, or the higher version has even higher dimension vector. And now it's all vectors that is going through. So whatever you write now are generate me carry select adder. Okay, generate RTL Verilog code for carry select adder. So all these words have converted into tokens, and tokens have converted into vectors, and every vector is a 4096 vector. So now these vectors, and this somebody has spent a lot of time in ensuring that the vectors, they are, if you go on this website, it's, so this is projector.tensorflow.org. Projector.tensorflow.org. Let's do it here. Projector.tensorflow.org. So you can visualize a dictionary. A smaller dictionary is just for academic purpose. You see this dictionary where if you put your cursor on a word, you will find out that how this is the whole dictionary. Okay, so this dictionary has 10,000 tokens, and the vector dimension is 200. Using principal component analysis, they have reduced its dimensions to 3D so that you can visualize. So if you place your cursor on any this extraction, and if you click on extraction, so it will have all its neighbors. So the closest is this a cosine similarity. You can have Euclidean similarity as well. Like extraction is in on the internet, once they were training this, it comes with ore, removal, extraction, removal, extracted, mining, coal, extract, cement. So all the words that on the internet, once they are training, making this dictionary in the vector space, whatever is closer to this word, so that once you find out the self-attention, and if any of these words is used, so it will give high correlation values that this word, these words are related. So perhaps extraction means the mining, and so so you can have any of you can see like any word, linear, for example, linear algebra, equation, dimensional, differential, vector. So that's how they have built this dictionary. And here is the dictionary. So so this is what is once the embedding happens, uh, the vectors which are closer to each other will be in the same direction. So now what you want to do is that somehow every word in a sentence should be changed into a vector which has the essence of the whole sentence. A sense of the whole sentence. Every word has the color of the whole sentence. Was it says swam, I swam across the river. So it has the essence of the whole sentence. And that's the job of this whole self-attention mechanism, converting every vector into another vector which has a sense of the whole context, whatever you have, the whole context. So that's how, because now every vector gets converted into something where it is has the essence of this correlation. Though you cannot have a word, this is very interesting. You cannot have a word to define a sentence. Okay, you may, but usually you cannot have a word which says I swam across the river to get to the other bank. There's no river, but you may have a vector which has a sense of I with other things. So that's why it is being converted into a vector, and you convert through the self-attention mechanism. You convert them every vector into another vector, uh, which has this whole thing, this essence thing, and then so these are the vectors that you keep on putting, going the different layers, and then finally they go through a fully corrected layer, then a softmax, and then they are going to generate a vector, which, keeping in perspective, the essence of all these vectors will point to the next word, which it has learned through all that training. So the attention is very simple now. It's just the dot product, because we know if A and B are closer, they have a higher dot product, and if they are far apart, they have a smaller dot product. Okay, so A dot B is just the dot product. How you compute the dot product? If it is two-dimensional, just 3 into 4 plus 1 into 1, and that's how you compute the dot product. So dot product computation is very simple. You compute the dot product, and so every vector dot product with every other. So V1 with V2, V3, Vn, then V2 with V1, V2, V3. And so every vector with every other vector, you compute the dot product. So one with one with two, one with three, one with n. So I swam across the river. Okay. So every word with every other word, dot product. Every word is going to give you a matrix. Okay. So N1, N2, N3, N4. So once you look at this is like bank. Bank is the last word. So you got to find out its dot product with I, with swam, with across, and you will find out there's very strong correlation with swam. Bank has a very strong correlation with the river. And obviously, bank has a very strong correlation with itself, which is going to be one kind of thing. So finding out all these correlations, and you will see a self-attention matrix like this, and you say, wow, so this is the self-attention matrix, where there is swam is this, okay, and swam is uh, I is this, swam across the river. So wide is high score. So river has a high correlation with swam. Swam has obviously highest correlation, and where you see the bank is score, but they are get is not so too high a correlation. So you're finding cross correlation of every of this with every word, and once you have this, so this is, these are the numbers that you get. These are the correlation of one with all, one with all, one with all. So just for S1, this is vector V1. You have its correlation with all 1, 1, 2, 3, 4, 5, 6, 7, and you get these numbers. And you can normalize this because it's an array, and you want to find out probabilistically which one is more closer to the other, and we know how to do the normalization, and that you have this kind of the dot product. You take exponential of the dot product, and then you have all the dot products combined, and you, so this will give you a probabilistic view of how these things are correlated. So this we call a softmax. Into the softmax, and these are the weights, which are the weights that which word is more correlated with the other. So now you have these weights. So these weights are for W1 is that how uh, it relates to rest of the words. Okay, and similarly W2 will have, and this will have these many numbers, that how they are just one number which says how correlated this vector is with the others. And now, because now you have weights, now you take these vectors and multiply them with the weights, and you get the same number of vectors. So you say, okay, now uh, this my v1 vector is converted into something which has now its correlation with rest of the word. So it is colored with rest of the words. So you have this y1 vector, which is first you are seeing how v1 relates to itself and with the others, and how much contribution of the other vectors with respect to their weights is in v1. So this y1 is now has the essence. This I is now changed into another vector which has the essence of the all the vectors with respect to itself, with respect to I, with respect to itself, what other how others are contributing. So is the y2 a sense of all the other, how they it relates to this. Now, so every vector has now, with respect to itself, has now the color of other words and how they are basically uh, contributing in making this understand what I is. So, so that's what you do, that you have all these vectors and now they are contextualized representation of the original vectors v1, v2, v3, vfn. Contextualized visualize representation of these vectors. Okay, so it has gone through these steps. So this is called the self-attention. So we have seen what self-attention is, and then we have seen that how you take these vectors and generate all these vectors. Okay. So now comes the where are the parameters, because there you don't see any parameters in them. So where are those training parameters and what is their role? So now here comes the learnable weights. So what you do is that you first, once you have this vector, you have a matrix and you convert them into three parts: a query, a key, and a value. So the same vector is split into three parts. And here this matrix are the weights. This matrix is 4096 by 4096, 4096 by 4096, 4096 by 4096. And you have, and why you do this, and then you do the multi-head attention. So now the things start getting more and more complex, but important is the same thing, that this vector that you convert, this all these vectors converting into these vectors should have an essence of the context, and the essence is strengthened by having the model trained on trillions, like 10 trillion words, sentences from the internet, and making them learn that how they are going to color these further beside what the embedding has done, so that these truly represent uh, the actual sense of the context, so that they once they generate the next word and the story, that must be comprehensible from all the learning they have done. Okay, so this is how this whole thing kind of works, that you have q, k, v vectors, and then you are going taking them up for this self-attention mechanism and generating another dot product attention, and a lot of other stuff, but primarily this. And these are the weights that we have learned, the parameters. And then there are like others, but these are primarily the parameters. I think this is kind of pretty much I want to do today. Maybe next time we will continue learning from here. And yeah, because this only will help you to have more, at least you know that how this thing is working, and then you will able to crank the maximum good out of a large language model. So thank you very much. I hope we are going to keep this.